All right, we're going to go ahead and move on to our second set of notes. This is going to be a little bit different because I need some props, so to speak, to teach this lesson well. It's also darker in here because I need to create shadows, which you should see in a minute. So I'm going to get to my globe back here in just a little bit. But to start us off, we're going to begin with notes number 2, day and night. All right, so I don't know why I just said that so funny. So for our warm-up, normally we would discuss these together in class, but the two questions that I want you to kind of just think about for a second is what is night and what causes it? And then what is day and what causes it? Okay. So if someone were to ask you for, a definition of what is nighttime, what is daytime? Okay. What would you say? Typically, and hopefully, most people would conclude or would come up with the answer that nighttime is when it's dark outside, right? The sun is not up, and daytime is when the sun is up and it's lighter outside. Okay, that's how we kind of separate our hours of the day and hours of the night, and that's generally a pretty good definition of the two. But we're going to go ahead and give our actual scientific definition of those two terms. Day is caused by exposure to the sun. Okay, so when you are in sunlight, it is the side of Earth facing toward the sun. Night is the opposite. It is the effect of being in Earth's shadow, meaning that this, as you can see in the picture, this side of Earth is blocking the light from getting to the other side. Okay, it is the side pointing away from the sun. So I'm going to turn off my light here, my lamp, and then it's just going to be dark in here. But I'm going to hopefully show you using my globe here a little bit more of what I'm talking about. Okay. So we're going to pretend that my flashlight here is the sun. Yes? Okay. So obviously the sun's not going to be, directly as bright as what you're seeing right here. But I have the United States right here on the map. Okay. Every once in a while, my Siri on my watch likes to hop on. So anyway, so this is when the United States would be in the sun. Okay, this would be daytime for the U.S. But you'll notice that on the back side of the globe over here, it is dark. Okay, that's the side of the Earth that would be in nighttime. All right. The issue though is hopefully you know that the Earth rotates or it spins on its axis. Okay, so at certain times, half the Earth is in nighttime while the other half is in the daytime. Okay, and this gives us the effect of night and day. Let's move on a little bit here, and I'll go back to my flashlight in a minute. Okay, so another term that we need to be familiar with is rotation. Rotation is when an object turns or spins around. Okay, so just like I was doing with my globe a minute ago, okay, when the object turns or spins like this is an example of rotation. All right. The Earth actually rotates on an imaginary shaft or like a stick, basically, called an axis. And this axis runs through the Earth from North Pole to South Pole. All right. If you can see my globe here, this is not technically straight up and down. It looks like it's tilted a little bit, like it's spinning off center. This would be straight up and down. Yes. Okay. However, the Earth doesn't actually spin like this. It actually does spin at a tilt. All right. And that imaginary, almost like if we could put a stick through the middle of the Earth, what it spins around. Okay. That would be called the axis, and it is kind of tilted to the side a little bit. It does run from the North Pole all the way at the top, all the way down to the South Pole. The axis leans at an angle of about 23 degrees. So what that means is if this would be like 90 degrees straight up, it's tilted this way 23 degrees. Okay, that little measurement of space right there is measured at 23 degrees. So the axis is leaning at an angle of 23 degrees, which is part of what gives us the seasons, as you'll see here in just a minute. Earth rotates on its axis counterclockwise, that's the direction it spins, giving an appearance of a sun that rises and sets. Here's where we're going to get to what we talked about yesterday. Or I can't remember when I assigned it, but in the changing shadows notes number 1. Okay. We talked about how it looks like to us the sun is actually moving from one side of the earth to the other, right? It's what it looks like. If you're standing here on Earth and you're tracking your shadow, all of a sudden the sun was on the eastern side and then it moves across the sky and now it's on the western side at night. That's what it looks like to us. But the sun is actually not moving, okay? The light source, let me see if I can do it like this without messing up my video, okay? The light source is actually in a fixed location, okay? What makes it look like the sun is moving is that the earth is actually what is rotating, okay? So let's go back to, here we are in Texas, okay? I've tilted a little bit so we're in the direct sunlight, all right? Pretend that you are actually standing on this globe, right? You are like a little person on this globe. And as it begins, as the earth is rotating, what do you see? Well, if you're standing here on Earth, right? We're all the way over here. Here we are. We're all the way over here. All right. As we start to come into the sun, it's almost like we're turning our head, right? We're looking right into the sunshine. Okay. So now, as the earth continues to rotate, now it looks like the sun is over here in the sky. And then it looks like it actually dips and it's gone, right? Okay. So day and night, that movement of the sun across the sky is not caused by the sun actually moving. It's us moving. Okay. The other way I can show this to you without breaking things, hopefully, is, hopefully you can be able to see me. Okay. So if we were to stand, okay, if I were standing facing the sun, move my little flashlight there. All right. Let's pretend I'm the earth, right? If the earth is the one rotating and the sun's over here in the corner of my eye, if I turn, all of a sudden now it looks like the sun is here and it's moving across the sky. To me, it looks like it's moving, but it's not actually moving. All right. You can actually test this at home on your own. If you go into a dark room and have someone hold a flashlight like this, okay, and then stand here, all right, and then spin like this, it will look like to you, if you didn't know you were moving, it would look like to you that the sun or the flashlight is moving across the sky, but it's not actually. You are the one rotating, okay? You're actually the one spinning on your own. So the rotation of the earth is what causes day and night. One complete rotation of our planet, okay? So one complete circle, here's United States, one complete circle all the way around, here we are again, takes 24 hours. That's why one day is 24 hours long. The other term we want to talk about is revolution. Now, people get revolution and rotation mixed up all the time, okay? Revolution comes from the word revolve, which means to go around something else, okay? Rotation is the object itself spinning. Revolution is the object traveling around something else. So revolution is different than rotation. This means traveling around something else. So the globe's going to be a little too big for me to do this with. Let's take, you know what? I think I have, let's try this. Okay. Let's take this for example. Okay. We're going to pretend the flashlight is still the sun. All right. Here's the earth or another object. Revolving is this object moving around. Notice I'm not spinning this. Okay. This is not spinning like this. That would be rotation. Okay. If I keep it facing forward like this, revolving is just moving around something else. Okay. Typically, if we were in the classroom, I would have you stand up behind your chair and I would say, okay, I want everyone to rotate. Okay. Well, then everyone starts spinning around like this. Rotating, spinning, rotating, etc. Okay. Then I would say, okay, stop. Now I want everyone to revolve and around your little desk pair here. Okay. Then everyone would stand straight facing me and they would move around their desk, kind of like this. Okay. If I were to kind of revolve my chair in a circle. Okay. That's the difference, rotation and revolution. Now, it takes 24 hours for the earth to make one rotation, but For the Earth to make one revolution around the sun, it takes 1 year, which we know is 365 days. Now, you may have heard this before, but it actually takes a little bit longer than 365 days. It actually takes 365 and 1/4 days. Okay, so this is the explanation of leap year. All right. Hopefully, you know that every 4 years we have a leap year where February has 1 extra day. February, instead of having 28 days, has 29. That's because every 4 years, okay, we have that 365 and 1/4, that little bit of 1/4 left over. Well, every 4 years, those 1/4 add up to 1 full day, right? 1/4 plus 1/4 plus 1/4 plus 1/4 gives me 4/4, which we know is equal to 1. So now I have 1 extra day every 4 years because that 1/4 adds up over time, and now I have 1 extra day on the 4th year. Okay, that's why we have a leap year every 4 years. Now, the revolution that the Earth, the path or the orbit, basically is what's called, that it takes around the sun is nearly circular. It's not actually a perfect circle. It's more like a squished circle, okay, like an egg shape. It's called an ellipsis, which is why you can kind of see in this picture here, it looks more like an oval, like a squished egg almost. It's not perfectly circular, which this also plays an effect on this with the seasons as well. The North Star, which the Latin name for the North Star is Polaris. You do need to have that. I believe it's also a blank in your notes. Double check. Yeah, the North Star, Polaris, is positioned directly over the Earth's North Pole. Okay, so I told you before, I'll bring my globe back here, that this North Pole, that the axis is tilted. Okay, so it's at about this angle right now. Okay, that's where it would be pointing. The North Star points the axis points directly to the North Star. So if I were to take a straight line straight from the axis and point it straight up, the North Star would be directly above. Okay, it's right above where the axis is pointing. The North Pole always points to the Polaris, no matter what the season is, whether it's summer, fall, winter, spring, day, night, any of the things. It's always pointing directly toward the North Star, which I believe you may have studied this before if you've been at Founders for a while, but I believe that's the star the Egyptians used when they built the pyramids. They lined up the pyramids directly with the North Star and they could do that because it never moves. It's always directly above the North Pole. Okay? Now, don't forget, the sun still changes position in the sky from east to west. Okay? It does, but not because the sun is moving, because we're moving. Okay? So it's still going to complete this pattern of moving east to west. Okay, here we are again over here. All right. It's still going to look like it's changing, but it's not because the sun is moving. It's because we are moving. The Earth is spinning. Okay. All right. One last thing I want to note before I have you do your 1-sentence summary. Okay. We talked about rotation and revolution. Okay. Now, what's crazy is the Earth does both of these at the same time. Okay. So while the Earth is spinning, it's also revolving. Okay. While it's rotating, it's also revolving. So the way I would have you show this would be if you stood behind your desk and I had you spin around in place, but then I also had you move in a circle around your desk. Okay. Try this at home. It's really fun. It's a little bit harder, but the videos that I have later in this pod will also help you understand that. So continue with the slides and follow the directions, and we'll see you next time.